Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will right away start with the idea of Hamilton's principle, and that is another point of discussion in our calculus of variation. So Hamilton's principle, Hamilton's principle or calculus of variations, and the key concepts that we will start discussing in this module will be the Euler-Lagrange equations, the extremals and the variational principles through those. Okay, so variational principles. Okay, so we will eventually we will use the fact that almost all physical processes are going to be governed by the variational principles in which a quantity becomes stationary. So what is that quantity? We will see that quantity is nothing but the Hamiltonian. Okay, so that is the basis of all motion, whether conserved or non-conserved. The basis of all motion is that the Hamiltonian is going to be stationary, or we call this as the principle of least action, or this is the foundation of the calculus of variations. So let me write down the foundation principle or the variational principle. The variational principle. Okay, so this is the principle on which it is possible to base the whole of classical mechanics, right, or the so-called Hamilton's principle. We will denote Hamilton's principle in shorthand notation by HP. Okay, so HP. So Hamilton's principle says that for all kinematically possible motions which takes the system from one configuration to another with a given time interval, the actual motion is the one that is going to minimize the Hamiltonian, right? So we are trying, all the time in calculus of variations, we are trying to minimize a quantity in order to determine the motion, or the so-called the Hamiltonian of the system. So let me write down this statement. So of all kinematically possible motions taking a system from one configuration to another within a given time interval, we see that the actual motion is the one that minimizes this Hamiltonian. The actual motion is the one minimizing the Hamiltonian, minimizing the time integral of the Lagrangian, or the so-called minimizing the time integral, certain time integral of the Lagrangian. Okay, so Lagrangian. We will later on, so this is the Hamiltonian principle. This is the foundation of all calculus of variations, and sometimes this is also known as the principle of least action. Okay, so then So we are essentially all the time, as I just said, all the time we are concerned about minimizing or maximizing this integral functional, not function, because functional is going to be the function of functions. So we are now introducing the concept of functional. So the calculus of variations, so COV, the calculus of variations, uh, tells us that we are concerned with minimizing or maximizing the integral function, the integral functional. Okay, so functional, the Lagrangian is a function of functions, so the integral will be an integral functional. Okay, so let us quickly look at some examples. It will be fairly clear what sort of problems we are dealing with. Say, for example, we are talking about the simplest example is finding the shortest path between 2 points, or the commonly known as the geodesics problem. So the shortest path, or the geodesics. So finding the shortest path, the problem is we need to find the shortest path connecting 2 points. The shortest path between 2 points, and intuitively the answer should be fairly clear. The shortest path, that is shortest in terms of length, will be the straight line, and which means that this is typically a problem with no constraints. We can there is no constraints involved, and if we were to write the math formulation of this shortest path problem, all we need to do was to minimize L of y, which is given by the integral from a to b ds. So this is integral a to b, integral from of square root dy dx square dx. Okay, so that is what we have. So then example, suppose we have that a is from 0 0 and we give 2 points 0 0 and 1 comma 0. So we see that y of 0 is 0 and y of 1 is 0, and we see that from here we can find that L of y is simply the line y equal to 0, right? It's as simple as that. And then another example could be geodesics on the geodesics on the sphere. And if we were to redo this problem with the variables theta and phi on the sphere, we will see that the geodesics on the sphere is the great circle, or the circle which passes through the diameter. So geodesics on sphere surface will be the great circle. Okay. So then let us look at slightly more involved problem, more complicated problem. The third problem that I want to highlight is a problem involving two variables. So the problem involves the finding the shape of some surface. Let's say we have 2 points, let's say A and B, on an axis. The axis is the axis of rotation, and between the 2 points we hang a rope, or let's say we have a soap film, right? And then we rotate this axis. The question is, what is the corresponding area of that the soap film forms? And so that is what we want to find. And just again, since this is a math discussion, I just want to introduce barely minimum physics here. The main physics tells us that the area, the nature tells us that the area of this soap film is going to be minimized, such that the surface tension of the soap film is minimized. So we have to find some sort of a minimum of this in this problem. right? So let us say, so this is the case of a soap film problem, and we see that, let us say, two rigid bodies, two rigid circles of radius b, and same axis of symmetry are fixed at a distance 2a, right, from each other. Then a soap film is then created. A soap film is created, which is going to span between these two wires. Let's say these are wires or spans between the two wires, right? And now the soap film forms the surface of revolution with two open ends. Okay, so that is clear from the diagram. So this question is, what is the shape? So we have to find the shape of this resulting film of rotation, right? So we clearly understand that this is the case. We first of all, it's a case of soap film, so let us neglect the weight of the soap film. So the only force that is acting on the surface of the soap film is the surface tension, right? So let us say we are talking about the negligible weight, and in this case we find that only we have the surface tension effect, surface tension effect. Okay, so we minimize our area AY, which is given by in this case it is going to be y being the distance from the axis of rotation, and let us say ds is the small length element of the soap film. So ys is going to be the area. So the minimum that we have to find is integral of y ds. Now if we were to, let us say the ds spans from some point minus a to plus a, right? So the distance is fixed, which is 2a, so minus a to plus a, and we see that this is going to be 2 pi integral from minus a to plus a y square root 1 plus dy dx, right? Square dx. Okay, so then so this is the functional that we want to minimize, and we can also impose some sort of a endpoint conditions, that is y at plus minus a is equal to b. So these are the constant conditions at both the ends. Okay, so that is the radius of the rotation. Okay, and typically we will see that in this problem the shape that we will see is the soap film forms the so-called catenary. We will see some of these examples later on, and it has these this U-shaped structure when the surface tension is minimized. Okay, or we mathematically when we solve this this functional problem. Okay, so then another problem that we can quickly discuss is finding the cost or reducing the cost of manufacturing, right? So reducing the cost minimization problem. So the problem says manufacturer's cost minimization. Okay, so suppose a manufacturer tries to produce some item and not only we have to reduce the cost of production, but we also have some sort of a storage of the item. The item is not sold overnight, so there is some sort of a storage involved. So that is, we have to minimize the net cost. So how to set up the integral in this case? So manufacturer produces volume X in time t, and let my x of t be the volume produced with cost alpha plus beta of x dot, with storage cost given by gamma of x, right, per unit time. Okay. So then what is the case in that setup? So how is the Lagrangian setup? So in that case, we have to find the total cost, which is going to be some integral, which is going to be the function of this volume produced, so 0 to x, and let us say that the volume produced is the function alpha plus beta x dot, and then plus we have to also add the storage cost, so gamma of x, and now this is per unit time, and the first cost is per unit volume, right? So we have to segregate the two integrals because the limits will be different. So this is dx plus integral 0 to t gamma of x dt, and now what we have is that c of x. Well, I can rewrite this first integral as this is going to be integral 0 to x alpha plus beta x dot times x dot plus gamma of x, right, and this is dt. So then so I have just simply used chain rule here. So then what we have is x of 0 is 0 and x of t is x here. So those are my endpoint conditions, and so that is what my functional is, which we have to minimize. Okay, so now let us try to revisit our Euler-Lagrange equation, and from there we are going to derive the necessary and sufficient conditions for the principle of least action to be true. So what are we going to do? So we will revisit our Lagrange equation, and from there we will find the principle of least action, or the so-called the Euler-Lagrange equation. Okay. So let us term the functional. So let me call this any arbitrary functional that we want to optimize is given by integral from x to b f of x comma x dot comma t dt, and this is going to be the variables. Well, again, we assume that all these argument variables are independent, right? So we want the goal of this problem is that we want to find x star, which is such that j of x star plus h is greater than or equal to j of x star, and this is for all admissible variations h. Okay, so we have that in this case x of a is a, and we put the conditions x of b is capital B, right? Well, or in other words, we can assume that these quantities h satisfy the endpoint conditions, that these variations h are 0 on the edges, right? So h of a is equal to h of b is equal to 0, right? And then what we find is that j of x star plus h minus j of x star. So let me try and rewrite this difference. We see that from our definition of this functional, we see that this is going to be integral from a to b h times partial f partial x at x star comma x star dot comma t plus h dot partial f partial x times x star comma x star dot comma t, and then we have finally the order in terms of h and h dot square. So higher orders, we are going to neglect those quantities, right? So I have expanded the integrand of this functional in the form of Taylor series and written out only the linear term, right? And so the higher order term are the first term going to be the quadratic term in the higher order term. Okay, so then now I am going to do a slight trick here where I am going to rewrite one of these expressions in this integrand. We see that, notice that h dot partial f partial x dot is going to be, well, if this is the integral we are talking about, this one, we can do an integration by parts. We see that this is also equal to h times partial f partial x dot. So this is our first function. So at x equal to a to x equal to b minus integral h, the second quantity in integration by parts. This is partial f partial x dot at x star comma x star dot comma t, and this is going to be dt, right? So then what we have is this is x from a to b, and the first quantity in this integration by parts can be set equal to 0 because here the variations will be vanishing at the end point. So h of a is equal to h of b equal to 0, right? And then what we have is that let us now plug it back into our integral equation, and we see that this particular difference j at x star plus h minus j at x star is going to be integral a to b partial f partial x minus d dt partial f partial x dot, right? And we see that this is times h dt. So we have clubbed everything. We have taken integration by parts on one of the terms, the second term, and now we are left with this particular integral plus whatever the remainder is, order h square. So then we let us call this expression 3. Notice that we want to minimize this difference, right? So let me first now introduce the idea of what do we mean by stationary functional definition. So stationary functional. So what we have is a function x star is said to be make a functional. So we are simultaneously we are describing the stationary functional as well as the critical point. So x star is said to make a functional g of x stationary if j of x star plus h minus j of x star is going to be this remainder term. Essentially we are saying this difference is 0 up to the order of accuracy order h square, or this is when the error is small, when this is small, right? And this is when we call that J is stationary. So J is, this is when J is stationary, or when H is linear. H is linear in 0. Okay, so okay, so H is linear. Okay, so so that is the idea when this functional is going to be stationary. So now we want to minimize this functional J of x star. So the concept is we want to minimize J, minimize this functional. So we want to find, so alternatively the statement says that we want to find this x star such that J of x star is always greater than equal to J of x star. X star plus H is always greater than equal to J of x star for all H. That is the x star we want to find. That is the critical function or the critical value that we want to find for this functional. So we want to make this this argument in this expression 3 to be non-negative. If that is the case, we can always replace H by minus H. Here, if we replace H by minus H, we can see that the first integrand has to be also this particular functional integral has to be satisfied for all variations H, right? And if we replace H by minus H, or some other scalar multiple of this perturbation H, then we also need to retain it. Imposes that we need to retain this inequality, right? So if we replace H by minus H, for example, this inequality is retained, and that is only true when the integrand inside this expression 3 is 0. So this is only possible when partial f partial x minus d dt of partial f partial x dot is 0, right? So that is the case, and that is where we have arrived at the so-called Euler-Lagrange equation. So we will just say that when our functional, let us go back to the previous slide, when our functional is of this form, where the integrand is given by this f, function f, we would like to find the critical function x star, which makes this functional stationary, and that is given by this equation, which is given by this let us say number 4. We call this equation number 4 as our famous Euler-Lagrange equations, and this is the starting point of our system which we will be solving. Okay, so then, so what have we got? So I think we have few more minutes. We will just state the statement of the Euler-Lagrange, and we will just state the criteria, the necessary condition, the sufficient condition, and so on and so forth. So the Euler-Lagrange equation says that g of x is stationary if the integrand is 0, right? And that is the case when partial f partial x minus d dt of partial f partial x dot is 0, or the Euler-Lagrange equations. This is what we get from the Euler-Lagrange equations. Okay, so this is an if and only if condition, and this is when this is the condition which makes the functional stationary, right? And this is when Euler-Lagrange equations are satisfied. Okay, so well, all it says is that we are going to find an extremal function. We are not just saying that we are going to find the minimum or the maximum of the functional. That is for the second variation, that is beyond the scope of this present course. We have to look at the second variation of the functional. right? So that is something, that gives the idea. So what I just said is x star is the extremal, right? It is not the minimal or the maximal value. We have just, this is, listeners can directly relate x star with the regular calculus where we do the first derivative test, and the first derivative test only gives us the critical point. So it is equivalent to that notion of a critical point. We haven't found what is maxima or minima. Okay, so let us quickly wrap up our discussion with one particular example. Let us say an example is as follows. So we want to find, so this question says, is the extremal j of x given by integral from x dot square by 2 by 4t dt with x of 1 equal to 5 and x of 2 equal to 11, right? Is this extremal going to be minima or maxima, right? So this question says, well, let us just simplify this problem. Find the extremal of this integral. So of course, our function inside the integrand f of x comma x dot, this is the function of one variable, is x dot square by 4t, and this is going to be, let us now differentiate. So our Euler-Lagrange equations, well, let us first find what is partial f partial x. So this is going to be 0, and partial f partial x dot, this is going to be x dot by 2t. And we see that in this case my Euler-Lagrange equation is d dt of partial f partial x dot, which is x dot by 2t minus partial f partial x, which is 0, and this is also equal to 0, and we see that in this case x is ct square plus d, right? And from here we see that we have some endpoint conditions also. We are given that x of 1, I think here we are given some endpoint conditions. So x of 1 is 5 and x of 2 is 11. So we can find these values of c and d. We see that the final equation is 2t square plus 3, right? So so this is as simple as following, finding the extremal. So I think I'll end my discussion at this point, and in the next module we will look at specific cases of Euler-Lagrange equation, namely the case for autonomous versus the case for non-autonomous system, and see how the Euler-Lagrange equation simplifies, especially in the case of autonomous system. So thank you very much so far for listening. Thank you.